Hi. In the next couple of minutes, I want to talk about a course at Jönsseklang I designed, Software Engineering for AI-Enabled Systems. It's only going to be a short pitch, but we want to talk about how we teach software engineering for systems that have a machine learning component in them. So it's specifically not taking the role of a traditional machine learning course where they are mostly focused on either understanding how machine learning techniques work or applying them to specific data sets to get models with high accuracy. We want to build real systems. We're also not really interested in applications in software engineering like you see at this conference because we think auto-completion and things like this are not really representative of what our students go out and do later. So the applications that we are thinking of are building machine learning components into systems that might actually be used by end users or companies, like PowerPoint, where they introduce this mechanism of design ideas to automatically lay out your slides. So PowerPoint is more than just the AI component, right? This is an AI component in a larger system. And another example is Temi, a transcription service, where you upload some audio files to get a transcript. So again, there's a machine learning component here, and it's a very important part of this. But just building the component doesn't get you there if you want to build a business. Right? So you need to think about the user interface, about scaling and accepting lots of audio files and storing them and dealing with mistakes and taking payments. So all of these things that correspond to building an actual system around this. And to build these kind of systems, you need the expertise of data science who can do the models and software engineers to actually build robust systems. There are lots of problems that come with AI components, like missing specifications, feedback loops, and so on and so on and so on. But we also argue that software engineers have a lot to contribute to building these systems. For example, we have a lot of experience of building safe systems from unreliable components. We have a lot of experience with risk analysis and requirements at the interface between the world and the machine, and so on. So things that we can actually teach here to help students to build these kind of systems when they go out into the real world. The course is structured around the traditional life cycle, thinking about how do requirements and testing and architecture change when you introduce machine learning components. And we would argue that a lot of this is much more an education problem, really thinking through and applying techniques that we already have, rather than a research problem where you need to identify completely new techniques. There's some of that as too, but the dominant part here, I think, is education. Just briefly at the end, we want to get away from these notebooks and static data sets and just evaluating accuracy. And this is reflected in our assignments as well. We built an infrastructure to simulate the real world where 1 million users, simulated users, are watching movies and students provide a recommendation service. This way, the recommendations that students have actually have an impact on the simulated real world. So we can detect feedback loops. They also need to run and operate the system in production. We look at availability. They need to update this with little downtime and so on. So we're creating realism here in terms of actually building a system. So if any of this is interested, we welcome you to look at our materials. We share all slides, assignments, finals, video recordings, and so on under a Creative Commons license. And we hope that this is useful to you or some of your students.